Thank you very much. It's a great pleasure to be here. It's my first time ever in Scotland. So it's been going great, except my understanding is that it doesn't actually stop raining until August. Is that right? Coming back right? So the title of my talk is Warm Glass Stickier Than Cold Glass? I have a number of graduate students and postdocs, and I feel that part of my job, besides teaching them how to do experimental physics, is teaching them how to sell their experimental physics, how to present their work to the public. And I tell them that having a good title is very important. You want to have a title which is not too stuffy, not too formal, which seems maybe a little quirky and sort of pulls you in. On the other hand, you don't want to be too over the top, too hysterical, it's too totally crazy. But I thought warm glass stickier than cold glass was just a little bit too formal, so I tried to see if I could come up with a good compromise here. Let's see. Oh, that's more like it. Is the catastrophic implosion of the universe, is it coming sooner than you think? And this is really, in a real sense, is a talk about quantum optics, so it falls quite nicely after Roy's talk here. It's musings and measurements of the uncertainty principle now applied to electric fields. Heisenberg's uncertainty principle says it's really hard to sit still. If you're a particle in a bowl, you can never really have zero energy, because to have zero energy, you'd have to be exactly no motion at all, no kinetic energy, and you have to be right in the center of the bowl, so you have no potential energy. But then, of course, if you were doing that, then you'd know exactly where you were and how fast you were going, and Heisenberg says, no, you can't do that. So really, it's Heisenberg who gives us what's called the zero-point energy. If anything that oscillates, basically, out there, if it oscillates at all, it's always got exactly 1/2 times Planck's constant times nu, the frequency of whatever little potential you're confining that thing in. And that's true for particles in a bowl, and it's also true for guitar strings. So we have the quantum mechanics of guitar strings. Even at zero temperature, every single mode, if you have a guitar string, it's going to have its fundamental mode. It's going to have, that looks like the 3rd harmonic. There's probably the 20th harmonic. Each of those modes, every possible or orthogonal mode of that guitar string, even at completely zero temperature, is always going to have at least 1/2 times h times nu worth of energy. And for guitar strings, there's actually 2 different modes. There's the mode which is sort of vibrating up and down, and there's another mode you can't see that vibrates in and out of the wall there. Each of those modes has got 1/2 times h times nu. It's just a small amount, a tiny amount of energy. Planck's constant's a small number, but it starts to add up because there are a lot of different modes of a guitar string. Turns out it doesn't just apply to particles or guitar strings, it applies to oscillating electric fields. There's a sort of a version of Heisenberg's uncertainty principle that says you can't simultaneously know how big your electric field is and how fast it's changing, and that gives rise to something very much like a zero-point energy, except for the electric field. So every possible mode of there's a particular mode of the electric field traveling along there. Every mode you can think of has got that small amount of energy, 1/2 times h times nu. If we were to approximate this auditorium as a rectangular prism, which is not quite, it's got a little slope here which is going to make the math a lot more difficult, but imagine it were just sort of flat and the walls were conducting. Then you'd have one mode of the electric field where the electric field sort of vanishes at this wall, comes to a maximum, and it'll vanishes at that wall. And there's another mode that comes like this, and a mode that comes like this, and then you can describe the particular mode of the electromagnetic field where you've got 500 nodes in this direction, 1,000 in this direction, 20,000 in this direction. You can add them up, and by the time you get to a few million modes, you get a lot of nodes. You can get a lot of different modes. So, for instance, light traveling. If you had imagine you had sort of reflecting walls in there, and you had a light beam bouncing back and forth between this wall. I don't know what it is. It's a certain number of meters. It might be about 30 million, maybe 30 million little nodes that way. But you could have a mode going that way. A lot of modes, the electromagnetic field. Okay, each one of those has got that zero-point energy. Okay, so I'm tired of talking about Heisenberg. Who's another physicist we can talk about? How about Einstein? What Einstein said is that E equals mc squared, and that applies to the gravitational field. So basically, the only thing I could find in PowerPoint that looked like a spaceship is this little icon here. I have a little box like this, and my spaceship goes zooming by. As it goes by, it bends a little bit. It's experiencing some gravitational attraction. If it goes by that box, it bends a little more. That means there's got to be more mass inside there. Well, it could be more mass, or according to Einstein, it could be more energy. Energy has its own gravitational energy, so it might be that it has its own gravitational attraction. So it might be the reason I'm bending as I go past there is there's some energy inside that box. So that's Heisenberg and that's Einstein. We can put them together. How much is the 0-point energy inside of a cube? 1 meter on a side. So we're going to add up all the electromagnetic modes inside a cube, 1 meter on the side. And to make it fair, I'm going to impose a maximum frequency, which is the frequency at which a photon has enough energy to split apart into an electron and a positron. So we'll have a cutoff at 511 keV. And it turns out to be 10 to the 28 kilograms. It's a vast amount of energy. To take the energy, if I divide it by c squared, then I get 10 to the 28 kilograms. So we put those two things together, and we get quantum mechanics plus general relativity equals sklooch, we're all dead. Sklooch, what does sklooch mean? Sklooch is the sound of the universe imploding on itself. It turns out that the electromagnetic field energy inside a cubic meter is about 10 to the 28 kilograms, which is also just the amount of mass you need to have inside a black hole with a Schwarzschild radius of 1 meter. So basically, 1 meter has already enough oomph inside it, so the whole thing ought to implode upon itself, so that we're all imploding. Okay, so now we've integral, and I subtracted away an infinity, which is something the theorists tell me about, and I found that, sure enough, there's a particular functional form to the shape of this the strength of the fluctuating electric field, and it follows the right power law. And I actually did the integral, and I got the force, and it turned out that it was in a factor of 2.5 of the right answer. And I was so very proud of myself for having done an integral, and just like a big boy, and I didn't really require a theorist to help me or anything. The only problem is this is the force is going to be proportional to the electric field square, which is a positive number. That polarizability is a positive number. That negative sign is real. After I did my calculation, what I discovered is that this atom is going to be attracted to regions of larger force. And I actually got the sign wrong. Basically, when I did this integral, I found that the Casimir-Polar attraction was a Casimir-Polar repulsion. So I was a little abashed by that. It turned out I'm not as good a theorist as I thought. On the other hand, I thought maybe this is a ray of hope for all of humanity. Maybe this fact that my calculation doesn't agree with the known fact that if you put an atom close to glass, it's attracted. Maybe this is the discrepancy that will point us, the loophole that will allow us to avoid us all getting scrunched down into a walnut by gravitational implosion. No, it turns out it's not that. What I neglected is several things. One is that if you have a piece of glass, some modes come in from the outside and bounce off, but you also have modes of the electromagnetic field which are inside the glass. And in particular, you have modes which hit the glass at glancing angle and bounce back in, total internal reflection, which has a little component of the electric field called an evanescent wave. Those waves have a local maximum in the electric field at the surface, as opposed to waves coming in at normal incidence, which have a local minimum when they bounce off. And then it turns out there's also waves from the exterior that some of those polarizations have a local maximum at the surface. So by the time you include all these different modes, it seems to be okay. But it is the case that if you just look at the outside waves, or just look at the inside waves, they contribute with opposite sign, and they almost cancel, and it actually suppresses the size of these modes. If you were to, one of the Italian guys pointed out to us is that if you were to change the temperature of these fluctuations, we can think of them as quantum mechanical fluctuations, but you can also get a thermal contribution if you're not at zero temperature. If you change the temperature of the external waves compared to the internal waves, which you can do by heating or cooling your substrate compared to the walls of the chamber you're holding it in, you can break that near cancellation and very much change the strength or even the sign of the Casimir force, or at least the thermal corrected Casimir force. Just sort of review the theory and the vocabulary. At very short range, this force is usually called, between an atom and a surface, is usually called the van der Waals force. That's if you're within something like a wavelength The wavelength I'm talking about is the wavelength of the light that the atom prefers to see. It's resonant wavelength for the atom. Within that, the potential falls off as 1 over z cubed. Out in the Casimir-Poulder region, it falls off as 1 over z to the 4th. There's sort of a knee there. You could call that an ankle. Once you get out to a distance which is comparable to the wavelength of black body radiation, it now falls off only as 1 over z cubed. And what the Italian guys showed is that they really showed a new contribution, which is at very long range, the Casimir-Poulder force falls off only as 1 over z squared if the temperature of the substrate and the temperature of the environment are not the same. If you break that degeneracy, then you get this new extremely long-range force, or sorry, long-range potential that's falling off only as 1 over z squared. So we set out to look for that, really set out to look for the thermal corrections to the Casimir-Poulder force, because no one had really ever been able to see thermal corrections to either a Casimir force or a Casimir-Poulder force. They're hard to see. In order to get to a region where they become important, you have to be out a significant distance away from the surface, 5 microns, 10 microns, where the force is very, very weak. So you need to be able to measure a very sensitive force. You need to have a very good control over your systematics, because most of the systematic forces fall off more slowly than the Casimir-Poulder force. So at 10 microns, the chances are the dominant contribution is not going to be the Casimir force unless you're very careful. So we set out to look for these thermal contributions. The range we looked at, unfortunately, was such that we can't ever see a clean power law dependence, because these three regimes all sort of intersect around here. So we actually had to do the theory where we actually got not just the power law, but the numerical coefficient in front, and compare that with what we saw. So we had to work very closely with the theorists to understand exactly the polarizability of the atom and the surface and so on. We use a Bose-Einstein condensate, which is a very, very cold thing. Here are rubidium atoms at 400 nanokelvin. Here they're cooler, 200 nanokelvin. That's something like a pure little packet of rubidium atoms at 50 nanokelvin. And so when I talk about seeing the thermal corrections of the Casimir force, people immediately think that I'm talking about something going on at 50 nanokelvin. But that's not really what I'm getting at. As far as I'm concerned, this is a zero temperature object. And we don't have to do this experiment with a Bose-Einstein condensation. The fact that we have a Bose-Einstein condensation, a tiny little ball of cold atoms, really doesn't matter very much. We could just as easily do this experiment with a single atom, except that a single atom is hard to see. You don't get very good signal to noise. So you can do a more precise experiment if you do a little packet of maybe 50,000 atoms all at once. But you want those 50,000 atoms to be moving very slowly, so you can put them close to the surface and keep them there for a long time. And you want them to be all very close together, so you don't have to average over some spatial inhomogeneity. So you want a small ball of atoms very close together, moving very slowly. That turns out to be high phase space density, and the limit of that is a Bose-Einstein condensate. So we're using the Bose-Einstein condensate as call it a high brightness source of atoms, not because of its own miraculous properties. Our apparatus is an ultra-high vacuum chamber. You can't see a lot of detail here, but inside these tubes there's very good vacuum, and we move atoms into this chamber. We're gonna do a little blowing up just inside there. Inside there we've got a glass cell about 1.5 centimeters. This is 1.5 centimeters here, 6, 7 centimeters long. Inside the glass cell we have a little glass rack, and on top of that we have various highly polished dielectric surfaces of various different materials. We move the atoms in here, we cool them down, and we lift them up close to the surface, and we measure the attraction between the atoms and the surface. The way we measure that attraction in physics, when you want to measure something very precisely, the best strategy is to convert anything you want to measure into a frequency. In physics, the things we measure really best are frequencies and not forces. So our atoms are being held in a little magnetic bowl, and they oscillate back and forth with some very well-defined frequency. We can move that magnetic bowl close to the surface, and now the attraction between the atom and the surface, if you get too close, the atoms will actually stick on the surface. But if you're not too close, the effect of the long tail of that force is to change the curvature of the potential at the bottom of that little well there, which changes the frequency of oscillation. So we look for this to measure the we can set the atoms wobbling in this little trap, and if we get very close, it changes the frequency. It's very similar to some scanning microscopies where they're measuring the topography of surface by putting a little tiny vibrating needle close to the surface, and they see the change in that frequency, and that's how they measure that force. Okay, so the condensates are sort of long and cigar shape, which is nice because we make the long length of the cigar parallel to the surface, so most of the atoms are all within about the same amount of the distance. And then my graduate students did this. This is really great. That's animation for you. And then we shake them, and they oscillate back and forth. Do you want to see that again? That was really pretty good, I thought. Next I'm going to have them do it in 3D, and we'll show it in the IMAX here. We'll have it vibrating in and out of the page or something. After it oscillates for a little while, we take a picture, we measure the distance between the atoms and the surface, and we plot that as a function of how long we let it oscillate. This is 1,000 milliseconds here, and that's about, during that time, it's oscillated 228 times. And you can see that it's still oscillating very coherently and with the same amplitude. It's a very, very high Q, low damped mode, this oscillating in the magnetic field, which means we can see shifts apart in 10,000 quite easily. We can see very small shifts, and we convert that shift in the frequency. It's actually not directly a measurement of force, it's a measurement of the gradient of the force, because the gradient of force looks like a spring constant, and that's what causes the frequency to shift. Okay, so I'm going to go back a second. What I want to say about this is that the other thing I tell my students, besides having an interesting title, is don't bog the audience down in the technological details. And the really hard stuff you should probably sweep under the rug, because they're willing to believe that you did a hard experiment. But I just want to say that this was actually a really hard experiment. And I make something of a profession of doing hard experiments, and this might have been the hardest one ever. It turns out that once you start getting surfaces involved, you can get dirt on your surface, and the dirt can have electric charges on it, and if you polish the surfaces really smoothly and you use an iron grit, then you'll have little chunks of iron embedded in your surface, and that will attract the atoms. There were a lot of systematics a lot of work associated with getting the surface very clean, and then more important, proving that you had the surface very clean, proving that there were no electric fields or magnetic fields emanating from the surface, and it took 3 years. That said, we're going to jump over those. So between this slide and the next slide is 3 years. Pop, there, okay. Here we have the distance from the surface to the center of the atom, 6 microns, 7 microns, 8 microns. This is the fractional shift in parts per 10,000. And you can see as we get closer, a frequency shift turns on and gets stronger and stronger. The black line, which you might be able to see there, would be the prediction at 0 Kelvin. The blue line is the prediction at 300 Kelvin. And if you did a lot of fancy statistics, you might possibly be able to convince yourself that the data agree better with the blue line than the black line, but I don't really believe that. I just told you the systematics of the problem were complicated. Trying to see a tiny shift like that of just a few percent with data that are noisy like that, well, that's a sketchy thing to do. So we were able to see the absolute scale of this force and see that whether at 0 Kelvin or at 300 Kelvin, it's agreeing quite well with theory. But to go see the temperature correction to this, we had to do something else. What we did is we painted the top side of each of these surfaces with some black paint. And we came in with a laser through the glass wall of the vacuum chamber, and the laser was absorbed on the black paint. And the little chip, the little wafer, whatever it is, we had silicon, we had quartz, we had borosilicate glass, we had various different kinds of dielectrics. We would heat it up, and just the glass would get hot, because this glass rack here is a very good insulator, and there's vacuum everything. So we could have the walls of this glass container here could be at room temperature, 300 Kelvin, and the walls out here could be at 300 Kelvin, but the chip itself could be at 600 Kelvin, factor of 2 higher temperature. So very large gradients, mostly because the glass is a very poor conductor. So we can do that. And then what the theorist said is, well, at 0 temperature, you've got 1 we say 1/2 times h times nu. That's sort of half a photon, excuse me, 1/2 photon in every spatial mode of the field, inside, outside the glass, and inside the glass. But if we go from, okay, and then if you go to a wavelength, a longer wavelength, say 10 microns, and you're at 10 microns, or say 20 microns wavelength light, and you're at 300 Kelvin, you'll find that instead of having half a photon, you've got 1.5 photons, say, because now you have a thermal contribution to that fluctuations. So we were parked about 5 or 6 microns away. It turns out that where the sort of the steepness of the slope is there at about 1/4 of a wavelength, so that's about 20 microns. We had what should be a thermal correction to the force, but ordinarily you can't see it because you get the attractive, you get some forces associated with the light coming from the outside, which those are actually repulsive forces. You get other forces associated with the fluctuations coming from inside. Those are attractive. They largely cancel out. What we could do is by warming up the substrate, now the mean free path, basically the distance the photons can travel on here before being absorbed is only about 30 or 40 microns. So the photons are actually, being born, if you like, by spontaneous emission and then bouncing off the surface and then being reabsorbed. You have this sort of black body radiation internal to this, which barely extends out. We can turn that up to 600 Kelvin, and that no longer, now the attractive forces are no longer balanced out by the repulsive forces, and we can see this effect much more clearly. So here are the data now, lots and lots of data. I'm just going to show you the average version of that. So the blue points go with the blue line, the green points with the green line, the red points with the red line, and down here the blue points are at 300 Kelvin, the substrate's at 300 Kelvin, room temperature, and the environment's at 300 Kelvin. For the red line, we've got the substrate at 600 Kelvin and the environment only at 300 Kelvin. And you can see that instead of being a couple percent change, this is now a factor of 2.5 there. It's a very dramatic enhancement of the Casimir polar force arising now from these thermal corrections to them. Nobody had been able to see thermal corrections. Sorry? Okay. No one had been able to see thermal corrections to Casimir-like, Casimir polar, Casimir forces before, usually because the effects were only 1 or 2%, and then there'd be various systematic things. We were able to see it for 2 reasons. One is we're now operating in a much larger range. Instead of being, say, half a micron away, we're 5 or 6 microns away from the surface, which is comparable to the wavelength of these thermal black body radiation. So now the contributions from the thermal black body radiation are much larger. Also, we could see them because we broke this sort of accidental cancellation between the attractive forces and the repulsive forces in order to make the effect of the thermal corrections much bigger. And then finally, you go to that very large distance, the Casimir polar force is very, very small. Maybe the thermal correction to the Casimir polar force is large compared to the Casimir polar force, but both of them are falling down as a very large power of that separation. It's a tiny force, and other forces such as Coulomb attraction between crud on one surface and crud on the other surface become very important. And so we had to spend a lot of time thinking about how to make glass very, very clean and keep it clean and measure and prove that it's clean in these conditions. But that all done, we're able to measure these things and see quite a large effect. Oh, okay, there's the data one more time, now presented as at a particular distance. We just do it as a function of temperature. This is what you'd expect if you had both the environment and the surface and the substrate at the same temperature. If you have the environment and the substrate at different temperature, you actually start to see an increase. You can see that if you have if you actually take the substrate colder, the environment, the force goes down, and if you go to a limit where you heat the walls of the chamber and cool the substrate, you can actually go to a place where the force changes side to where you get the Casimir polar force becomes repulsive, which would be really cool to see. You can imagine the atoms just sort of wafting along the surface, being repelled by the Casimir force. Unfortunately, if you've ever done experiments in ultra-high vacuum, you know that if you have one little chip and one little surface in there, which is at cryogenic temperatures, and everything else is very hot, all the dirt flies off the walls of the chamber and it sticks on the glass. It's a way of sort of creating a maximally dirty surface. And so we haven't been able to figure out a way of doing those experiments. Okay, so let's review with some questions. Why hasn't the gravity from the energy of the zero-point fluctuation of the fields imploded the universe? Question 2, and caused us all to die. Questions 3, painful deaths. Although if it's any consolation, they'd be short deaths. But painful while they lasted. And the answer is, I really don't know. But I hope that we have come to understand a little bit more about the Casimir polar force, why it's attractive and not repulsive, and why warm glass is stickier than cold glass. And it all has to do with whether you're looking at the fluctuations which are coming from outside the glass or inside the glass, and how you can see the relative effects of these by changing the temperature. I thank you very much for your attention, and I'm happy to answer any questions.
So we have time for 1 or 2 questions.
Yes.
You mentioned that most of your apparatus is at 310 or 300 Kelvin.
Yes.
And yet you're putting Bose-Einstein condensate at 15 nanokelvin, right close to this other sheet of glass, which is now at 600. How do you manage to keep the Bose-Einstein condensate actually still that cold in amongst all this?
Yeah, it's a good question. How do we keep the condensate so cold? If you think about the environment, the glass being at 300 Kelvin, and typically the condensate might be 30 nanokelvin, that's 10 orders of magnitude difference in temperature across a 3 or 4 micron distance. Even logarithmically, that's quite a big gap, isn't it? The trick is it's a very, very good vacuum. And the other trick is that this black body radiation is not actually absorbed by the atoms. It can polarize the atoms, but so the atoms sort of feel some net average effect of the radiation, but it doesn't actually push them around, doesn't warm them up. If instead of using atoms, we tried to use like a tiny particle of dust or something, that would absorb that radiation, instantly get very hot. And then once you've gotten over that problem, it doesn't really matter whether you're a centimeter away, which is how we ordinarily operate, or a few microns away, as long as you're outside of the sort of range of the phonons in the surface. Right now we're at 5 microns. If we get down to, say, a nanometer or 5 angstroms or something like that, then the surface is actually vibrating, thermally vibrating, and that would shake the atoms like crazy, and it'd probably presumably pretty good heat transfer there. Yeah.
Well, if there's no more questions, we'll thank Eric again. Thanks very much, Eric.